Hey physics class. So last week we were doing equivalent resistance, which is all well and good. It's you know, moderately complicated, but once you get the hang of it, it just turns out to be almost like untying a knot or something. It's just following a bunch of simple steps in a long complicated procession. Well, that isn't just an end unto itself. The point of finding equivalent resistance is actually because it's an important part in analyzing circuits for other reasons. And for this, I want to bring back Ohm's law so that we can use it on more complicated scenarios involving actual circuits. So let me first remind you of a particular analogy that I want to use to kind of help connect this to something more comprehensible. So let's just remember, when it comes to circuits, that we have to deal with voltage, V, and we also have to deal with current, which in Ohm's law is represented by the letter I. And also, of course, we've got resistance, which in Ohm's law is R. Since it's been a little while since we had Ohm's law, let me actually remind you of the units of those. Voltage is measured in volts, so the units are V. Current is measured in amps or amperes, so the unit is A. And resistance is measured in ohms, and the symbol is omega. Okay, and just for good measure, let's make sure that we actually have Ohm's law on here somewhere. So let me stick that here. V equals IR. There we go. So we've got Ohm's law. We've got the three quantities in Ohm's law, the variables that stand for them, and then the unit. Okay, so what analogy am I going to use to try to help explain this? I'm going to use traffic on roads. This is one that I had used before. I'd used traffic and water. I think traffic is a little easier to understand because it's one that you're more likely to have experienced, or at least before you had to stop driving everywhere. So voltage. I like to think of this as the urgency with which the electricity is being pushed or pulled. And the reason that I like that concept of urgency is because even in the water analogy, water pressure is the analogy for voltage. And in the particular case of traffic, when I think of urgency, I think of something like, how important is it that I get to the destination now? Like how stressed will you be if the light turns red and you need to wait? That's the idea that I'm thinking of in terms of urgency. But if you can kind of get that idea in your head, that'll be good. So current is a measurement of how much electricity is actually flowing. And in the context of traffic, that would be like traffic volume. So if we were actually counting traffic volume, we would be counting it in terms of like number of cars per unit time. Like on a road, maybe 100 cars pass every minute. That would be a high traffic volume. That might not translate very well to electricity because we're not counting individual electrons. We're counting like a continuous quantity. But as long as you can draw that connection in your head between electricity flowing through a wire and cars driving down a road, then that should work. And resistance in the traffic analogy was kind of like the delay that a road causes, but the delay is caused by a difficulty. So a delay or difficulty of the road. Ooh, that's a D. Okay. Right. So when I'm drawing a circuit, I'm going to explain it twice, right? I'm going to explain it in terms of the traffic analogy, and then I'm also going to explain it in terms of the actual electricity. Okay, so just keep these in mind, and they will be the conceptual tool that we will use to make sure that we understand everything. So let's go ahead and do a fictional circuit. Okay, so every circuit needs a start and an end. I'm going to follow the model of the problems that I gave you, and I'm just going to draw the circuit with a start and an end like this. So I'm going to start here at A, and I'm going to follow a path to B. But obviously not the short way. I have to go around the circuit. So let's go ahead and start here, and I'm going to have a little fork in the road. And this is going to be the good road on this side, and this is going to be the bad road on that side. Okay, so after the split, they come back together, and we're headed back up to B. Now there is another stretch of good road here. Following that, another stretch of bad road, and then we end up at the destination. Okay, so let's analyze this from the traffic point of view. When you've got your armada of cars all leaving A and heading down towards B, and they approach this fork, I want you to imagine that they all have a good view here, as in they know what the traffic is like on the bad road, and they know what the traffic is like on the good road. And when I say the good road, you know, I'm talking about like a big 4, 6, 8 lane highway. It's well paved. There's no gaping holes in the road. It's an easy drive. The road offers very little in terms of natural hazards, so the drive should be easy. The bad road is twisty and windy, full of potholes, blind turns, so it's the kind of thing that can cause delays. It's difficult to drive down if you like, maybe it's covered in snow or something. So if you were to be driving and you come to this fork and you have a good view, as in you know what the traffic conditions and the road conditions are like on each of those roads, what would cause you to choose one road over the other? Now, your predilection might be, I want to go on the good road. But there actually is something that could cause you to prefer the bad road to the good road. Can you think what that might be? Well, a good example would be that the good road is already packed. Because if more people tend to choose the good road, they've caused traffic on it, making it so that the empty bad road is now actually an attractive alternative. So the fact is that most of the cars will go on the good road, but at some point the good road will become saturated with traffic, so that choosing the bad road is actually a good choice for some of the cars, simply because the inherent delays in the bad road kind of work out to be as bad as, or only as bad as, the traffic jam on the good road, because that's where most of the cars went. And that's typically how roads are designed. Roads that are more commonly traveled are made larger to accommodate more traffic, and as long as every road can handle the traffic that is on it, then the roads are all good. So what we will have is the cars on the good road and the cars on the bad road are equivalent in terms of their urgency. Okay? the cars on the bad road are going to be like, "Oh, this road's terrible." The cars on the good road are going to be like, "Oh, this road's full." They're full for different reasons. They're feeling stressed for different reasons. But the point is, if you were at this fork and you're looking at the good road and it's in total gridlock, well, then the bad road is a better choice. We're trying to get it so that they are equivalent choices. And that assumes that if you have a good view here, you will make a good choice. Okay, so the conclusions that we can get here is that the urgency is the same. Let's see, where do I have room to write this? I think I have room to write it right here. So the urgency is the same. However, the traffic volume itself will be different. Okay, let's move past that part of the road and let's go around the bend and go to this little stretch. Over here, they were in parallel. You had a choice about which road to take. Here, the choice is gone. You must go through both roads. So, the people who took this good road actually end up having a harder time on this good road because this traffic was lighter due to this option taking some of the traffic off. However, right now, that is as good as it gets. After driving through this good road, we're going to end up on a bad road, and all of a sudden everybody is having a harder time. Okay? You can almost imagine this like everybody on the highway, and now the entire highway got off at the same exit, and now the exit's backed up. So there's no difference between the number of cars that take this and take that. That's going to be the same. We're going to end up with the same volume. But what about the urgency? Okay, so let's say they're on time, they're on the good road, they're thinking, good, I'm going to make it. All of a sudden, they're all backed up on the bad road, and the urgency skyrockets. You feel different on this road than on that one when you have the same number of cars on it. So while we might have the same volume, we are going to have the urgency be different. Urgency, can I fit the word different? Different. Oh, that didn't go so well, but I said it out loud, so you know what I said. Okay, we're going to have this scenario play out, but with circuits, and I'm going to draw the same circuit, but I'm going to replace everything with resistors. Okay, so let's recreate this. Got my starting point, and then I've got a couple resistors in parallel. This one is going to have a low resistance. This one is going to have a high resistance. Let me actually put some numbers in there. Let me say this can be, let's just make it be 10 ohms, and this one can be 1,000 ohms. 1 kilo ohm. Okay, so let's have that circuit continue around. Follow up 2 circuits in series. And there's the end. Okay, so we have our good road first. That would be our low resistance resistor, 10 ohms. And then our bad road last. That would be our high resistance resistor, 1 kilo ohm. Okay. So here's what we're going to end up having. Just like before, the electricity is going to have an easier time passing through here, and a harder time passing through here. However, the electricity will split up so that most of the current is taking the easy way, and a little bit of the current is taking the hard way, so that the total urgency, that is the electrical pressure, is the same on both sides. So how does that look in terms of Ohm's law? Well, it just means that when you're solving V equals IR, these have two different values of R, but they will have the same V on them. And that means that they have a different I. I'll solve this mathematically in a second. I'm just trying to lay down the concept. V will be the same, I will be different. That's not I mean I. So V will be the same, current will be different. Okay, now let's move on down here. These two have different values for R, but since they're in series, they will have the same current, the same I, but the V will be different. So in order to make this circuit actually solvable, I'm going to need to put a battery in it. But before I go ahead and do that, can you just see the similarity to what was before? We've got low resistance resistor, good road, high resistance resistor, bad road. You get the idea? Okay, low and high, good and bad. It's a same idea. Okay, so let me just fix this circuit. I'm going to put a battery in it, and I'm just trying to keep all the math super duper easy, so I'm going to just put a 5-volt battery on it. So let me go ahead and do that. Okay, now it's a complete circuit, 5 volts. Okay, let's work out how this is going to work, and I might need to use some space elsewhere because I want to keep this visible, but I also need some room to do some math. So let's first find the equivalent resistance of this. We have a 10 ohm and a 1000 ohm resistor in parallel. The way that we would find that is that, here, I'm going to use a different color. 1 over the total resistance is going to be equal to 1 over 10 plus 1 over 1000. So let me go ahead and actually do that calculation. 1 over 1 over 10 plus 1 over 1000. Okay, so we have a 9.9. It rounds pretty well, so 9.9. That means that for the sake of equivalent resistance, I can kind of reimagine this as if there's just a 9.9 right there. So let me go ahead and do that. So I've got my 5-volt battery. Now I have a single big 9.9 ohm resistor, and then my 10, and oh, I didn't connect it. You get it. My 1000. Okay, so we can actually find the equivalent resistance of this entire circuit, and that is going to be 9.9 plus 10 plus 1000. So we've got 1019.9 is the equivalent resistance. We can go ahead and find the current through the circuit now. So if the entire resistance is 1019.9 and our voltage is 5, sorry, that would be ohms, that would be volts, we can actually find the current now, because if V equals IR, then I equals V over R, and that would be 5 divided by 1019.9. So let's go ahead and do that. Hey, calculator, why don't you work? Calculator. Okay, sorry, calculator is freaking out. 5 divided by 1019.9. Okay, 4.9 milliamps. That would be 0.0049 amps. So I'm just going to call that, you know what, let me keep it in amps because I don't want to deal with unit nonsense. So our total current in this circuit is 0.0049 amps. Well, that means that 0.0049 amps had to go through this resistor, and through this resistor, and through this resistor. That amount of electricity had to go through each of those resistors. Just like you could say that amount of traffic needed to go through these roads, and this road, and this road. That amount of electricity had to go through this resistor, which is made of, hold on a sec, which is made of these resistors, okay? That amount of electricity had to go through these resistors, represented by this resistor, and then that amount of electricity also had to go through this resistor and that one, 0.0049 amps. Okay? But this 0.0049 amps didn't get shared evenly between these two resistors. So, how much current went through each of them? The way that this works is it's going to be proportional to their resistance. Okay, so if you remember the problem from the beginning of last week, where I had 2 roads with different speeds, and we wanted to get all the cars to arrive at the destination simultaneously, the number of cars that would take one road versus the other, it had to be proportional to how much traffic the road could handle. And in this particular case, this resistor resists the flow of electricity 100 times what that one does, which means this one should have 100 times the current as that one. So let's just see here. The actual current was 0.0049. And we need to split that up so that one quantity can be 100 times the other. In other words, we need to split it up into 101 parts, give 100 to the easy road, give 1 to the hard road. So here's how that looks more rigorously. Let me get a fresh sheet of paper out here so I can draw this. Okay. So, in the situation where we have some current that's traveling through 2 resistors, resistor 1 and resistor 2, how much current goes through resistor 1? That is, what is current 1? How much current goes through resistor 2? That is, what is current 2? So here's how this is going to work. Resistor 1 out of the sum of the two resistors is going to be the proportion of current. This proportion is how much resistance does this contribute. So like in the other example, right, it was 10 and 100. 10 and 1,000. So that breaks down to, here, let me write that out. If you had 10 out of 10 plus 1,000, you've got 10 out of 1,010. Cross out the zeros. You got 1 out of 101. Oop, can't see that. There we go. 1 out of 101. So the idea is, if that resistor contributes only 1 out of 101 of the resistance, then it's going to get 100 of the 100 parts of current going through it. So this particular example is pretty simple because there's only two resistors, and I don't want you to confuse the shortcut with the real answer, but let's just go ahead and go with this. So if we're talking resistor 1 is only contributes this much of the resistance, then it's going to end up with it would be the total resistance minus its resistance. That would be like the 101 minus the one that it would get. I think in the case of two resistors, it might be easier just to go for the answer. So I'm going to do that. Get this paper out of the way. So here, let me move that to the side. There we go. So I've got some room to write that, and it's still in the frame. Okay, so let me use these colors. So let me name these resistor 1 and resistor 2. So if I put in a fraction resistor 1 plus resistor 2 in the bottom, that's 10 plus 1,000. We're out of 1,010. And so I've got my 1,010 minus R1. See, the reason I don't want to let you confuse the shortcut with the real answers, because if I just wrote R2 up there, you might think that it's somehow based on the other resistor. It's not. It's based on this resistor's relationship with the whole network. It might be easier to see if I did one with 3. So let me do that one after this. This is going to end up being 1,000 out of 1,010, which is 100 out of 101. So this resistor is going to end up getting 100 out of 101 of the total 0.0049 amps of current. Let's see what that is. Oops, clear that. 100 out of 101. Most of it, it's 99%, times 0.0049. Okay, so it actually rounds up to 0.49, but I can't do that because then I'll have 0 with a rounding error. So 0.00485. 0.00485. Let me go ahead and write that here. The current on this side is 0.00485. Okay, so how much is left for this one? Clearly, it's just the rest of it that makes it to 0.49, so 0.00005. Holy cow, that would be 1 out of 101 of 0.0049. Let me actually do that calculation just so that you can see it. 1 out of 101 times 0.0049. See? 0.4048. So that 48 rounds up to 5. Holy cow. That's not a lot of current. 0.00. Can I even fit that in here? I can't even fit that in there. 0.00005 amps. That is incredible. Okay, so as I'm doing this, it's occurring to me that this just got very complicated and abstract. And I'm not sure that the illustration so far has served that. So I'm going to summarize this again at the end because I don't want that to get lost. Okay, so we've got that current going through there. All right, now we need to go back to this picture. This was the whole circuit in series, and we know that 0.0049 amps went through these two resistors. It's just that like 99% of it went on the good side and 1% of it went on the bad side. But together it was 0.0049. Okay, so that much current went through all those resistors. What's the voltage across each one? So remember that voltage in our analogy is urgency, but in reality, voltage is an energy difference. And the idea is that it's going to cost electrons energy to pass through a resistor. And it costs less energy to go through easy resistors, and it costs more energy to go through larger resistors. In other words, we're looking at 5 volts all this way, and then after this resistor, the voltage will be less than 5 because some of the energy has already been spent. How much of it will have been spent? Well, it's going to be proportional to the resistance. So the total resistance of this circuit was 1019.9. How much of that resistance is in this resistor? Not very much. This particular resistor only possesses 9.9 out of 1019 of, sorry, 0.9 of the circuit's resistance. So let's see what that is. 9.9. Oops, that's plus. Sorry, they look kind of the same. 9.9 divided by 1019.9. Woo! So that's not a lot, actually. This resistor is only 0.0097 of the entire circuit's resistance, which means it's only going to use up 0.0097 of the 5 volts. So let me multiply that by 5. Okay. What we can say is that 0.0485 volts were dropped over that resistor, so that on the other side of that resistor, there's only, well, let's see what the difference is, 0.0485. So we've got 0.0485 volts over that resistor. Let's see. Oops. 5 minus 0.0485. Still a lot. 4.952. Just round that. So at this point, the voltage is 0.45, I'm sorry, 4.9515. Okay, how much of the voltage is lost here? Again, this resistor has 10 out of 1019.9 of the entire circuit's resistance. 10 divided by 1019.9, it's almost exactly the same. It's 0.0098. Let's multiply that by 5, and now we drop 0.0490. So yeah, I've got enough room to write that. So the voltage drop here is going to be 0.049. How much voltage is left? We started with, we started with 5 volts in the battery. We lost this much here, minus 0.0485. We've only got 4.9515 volts left. Then we go through this resistor. We got to subtract the amount that we lost there, which is 0.049. There's only 4.9 volts left, 4.9025. Well, guess what? That is the same proportion out of 5 volts as 1000 is to the resistance of the entire circuit. So let me go ahead and confirm that 4.9025. Let me write that down. I've already got some blue right next to that, so let me write that in orange. There's going to be 4.9025 volts over that resistor. Let's see. 1000 out of 1019. So 0.981. So we get 98% of the resistance in that resistor, which means 98% of that battery is going to be used up crossing that resistor. Oops. So let's just see how much that is. Times 5, 4.9. See? Okay, so we can draw this circuit one more time and make this all clear. Okay, I'm going to draw it slightly compressed so I have some room. So up here at the top, I got my 5 volt battery. There's my resistors. Okay. So I'm going to label these R1, R2, R3, and R4. So down below, I should have 4 resistors, R1, R2, R3, and just barely in the frame, R4. Each of these resistors has a value associated with it. They each have a resistance. There is a current flowing through each one, and there is a voltage across each one. The resistance of, I think I might need a finer pen to fit the numbers in there. Let's see if I can do that. So the resistance of resistor 1 was 10, and the resistance of resistor 2 was 1000. 3 was also 10, and 4 was also 1000. Okay. How much voltage was dropped over... Oh, why am I doing voltage first? Let me go ahead and do current first. So the same current went through these two and this group, but this group didn't share it evenly. So let me see. We know that it was there it is, 0049. That went through these two, 0.0049, 0.0049. That much current went through each of those, but these two had to share the 0.0049. And let's see, I just threw away the paper that I did the work on. Where did I do that? I did that somewhere. Where did I do that? Oh, there it is. Sorry. Yeah, that's ludicrous. So, resistor 1 ended up with 0.00485 of the current, and resistor 2 ended up with 0.405. Okay, so just to be clear, because resistors 1 and 2 are in parallel, they got a different current through them. However, the sum of these two currents equals each of those. Okay, as far as voltage goes, the voltage that got dropped is different for this group, but it's the same within the group. And that would have been 0.0485. And for resistor 3, that's it was close. It was slightly higher. It's 0.049. And for resistor 4, 0.049. All right. Well, so a couple things. This went long. And I don't think that this presentation actually is going to be very instructional, especially for a first time. So I'm not going to let this stand as a day's lesson. I'm going to have to release this kind of as unassigned to a particular day, because this is too big to do all at once. I need to break this down. Well, I think it's still worth something, so I'll still produce it. Anyway, good luck with this. Hopefully this was helpful and not hurtful. All right, we're out.